Structure and properties of ethers. The central atom, the oxygen, is sp3 hybridized. So that means it has a tetrahedral electron geometry. Our bond angle, then, should be somewhere around 109.5. Water is not an ether, but you can think of it as an analog. The bond angle in water is 105 degrees. That's because the two lone pairs repel more strongly than the two bonding pairs, or you can think of them as taking up more space. Either way, that shrinks the bond angle. The bond angle in methanol, however, is larger. It's up to 109 degrees. Why is that? Think sterics. A methyl group is bulkier than a hydrogen. The steric effect in dimethyl ether should be even greater, because now we have two bulky groups. So you'd expect this bond angle to be greater than 109. And in fact it is. It's up to 112 degrees now. With diterbutyl ether, T-butyl groups are much bulkier than methyl. You could expect this bond angle to be greater than 112 degrees. About the boiling point of an ether. This is a function of the strength of the intermolecular force. And the basic principle is a stronger intermolecular attractive force leads to a higher boiling point. And remember, attractive forces, LDF, tends to be weaker than dipole-dipole, which still is weaker than hydrogen bonding. So this is in direction of increasing attractive force. When we consider ethers, well, we have LDF. For light ethers, LDF is not the strongest attractive force. CO bonds are polar, carbon having an electronegativity of 2.5 and oxygen having an electronegativity of 3.5. You end up with a molecular dipole like so. So for light ethers, dipole-dipole is a big factor. Ethers, however, are not hydrogen bond donors. Remember, a hydrogen bond donor needs to contain an HX covalent bond, where X is nitrogen, oxygen, or fluorine. So even though an ether contains an oxygen, the oxygen is bonded to carbons and not to hydrogen. Hence, ethers can be hydrogen bond acceptors, which makes them soluble in hydrogen bonding solvents, but they are not hydrogen bond donors, so they won't have as high a boiling point, say, as an alcohol. So if we consider ethanol, dimethyl ether, and propane, all three of these compounds have similar molecular weights, so they have about the same amount of London dispersion force. Ethanol is an alcohol, so it's capable of being a hydrogen bond donor. Dimethyl ether has dipole-dipole as its dominant intermolecular force, and propane has LDF. We can see Ethanol has the strongest intermolecular force and therefore the highest boiling point. Propane has the weakest intermolecular force and therefore the lowest boiling point. The ether has a higher boiling point than the propane because of those dipole-dipole forces, but it's not a huge amount higher. Now let's account for these differences. As the size of the R groups goes up, the boiling point of an ether increases. All three of these are polar molecules. In dimethyl ether, the dipole-dipole is the dominant intermolecular force. In diethyl ether, the greater molar mass of the R groups now gives you an increased amount of LDF. And the LDF is still quite a bit higher for the dipropyl ether. So this is an illustration of the increasing importance of London dispersion force as the mass goes up. For an exercise, rank these from lowest boiling point to highest boiling point. Pause and work it. Since these all have comparable molecular weights, you're looking for the one that has the strongest intermolecular force. In other words, the one that has the most hydrogen bonding. Pause the video unless you've done the work. Here's my solution. Number 2 is lowest because it has LDF only. Next is number 5 because it has dipole-dipole. Number 3 is next because it's capable of participating in one hydrogen bond as a donor or an acceptor. Then number 4 because it's got dipole-dipole and hydrogen bonding. Number 5 because it's capable of participating in hydrogen bonds at 2 sites simultaneously as both a donor and acceptor. So 5 should have the highest boiling point, 2 should have the lowest. Whoa, excuse me. 1 should have the highest and 2 should have the lowest. In terms of solubility, well, alcohols are hydrogen bond donors. Ethers are not hydrogen bond donors, but their polarity makes them hydrogen bond acceptors. So, ethers will be soluble in any solvent that is polar or a hydrogen bond donor. And then ethers of large molecular weight will be soluble in nonpolar solvents where LDF dominates. So to summarize, ethers will be soluble in protic solvents because they can act as hydrogen bond acceptors at the protic site. And they're soluble in polar solvents because of their dipole-dipole force. Ethers will even be soluble in nonpolar solvents because of their hydrophobic portion, and that increases as the molecular weight of the ether goes up. Because ethers are good solvents themselves, because they're polar aprotic, they're great for SN2 reactions. Right, so here's diethyl ether, an acyclic ether, and tetrahydrofuran, a cyclic ether with 4 carbons, and 1,4-dioxane, another cyclic ether. Well, it's a cyclic diether. All of these are good solvents for SN2 reactions.